driving cars. There's all kinds of information that you got to have. Detect the brake detection, the proximity of the car, where it's going to go, where it's going to stop. Already in my car, there's the side lane warning system, right? That's getting pretty common. By the way, it's a number of students in my class create a potential startup for that. So new cars come with those kinds of activities, all kinds of features, but cars that were made previously, they don't have those, right? So if you now create an aftermarket solution that is able to attach, the first time you might think of, well, okay, so I can buy a sensor and I can put sensors on the side of the car, but integrating those into the automobile is not easy. So one opportunity I'll just throw out is if you have a sensor that integrates to an app on a smartphone, then your smartphone will beep when you're trying to shift lanes, right? That could be a solution. Now, it's not what I think, it's what the customers will think, right? So you gotta, if that's something you want to follow up on, go find out how you might do something like that. Don't actually build anything, but go check with 10 of your colleagues, 10 of your buddies, if that's something that don't have it in new cars. See if that's something that is a problem that's bothering them, and if that's a solution that might be of interest to them. That's how you decide whether to do a startup or not. But the opportunities are there, is what I'm trying to show you here. That was one of the surround view, the blind spot detection. There's a rear collision warning system, again, in the new cars that comes integrated, parking assistance, so all kinds of things in the automobile. The 5G, of course, is going to be able to let you do remote surgery, for instance, and that might require lots of data transmission, a lot of security, a lot of sensitive information to be processed. Today's wearables, though, lots of people have wearable devices, but they're really kludgy and they're clumsy. So maybe they're not getting as popular as you might like them to, but one way to look at how you might want to do best in class is to do new techniques of doing biosensors, or non-invasive electrochemical glucose sensors, for instance. There's a startup in San Diego that's doing exactly that for diabetes monitoring. And so that might require new technology, new packaging technology, new chemical technology, new detection technology, so all kinds of interesting stuff that could be conceived. Now, whether there's a market or not, again, I'll just keep saying that it's determined by the potential customer. If there's a problem you're solving, customer wants it, they're willing to pay you enough, then it makes sense. Ultra low power bioelectronics, so if you're, again, an analog field or whatever, doing ultra low power design is extremely important. You can go to ISSCC or any of the conferences, a lot of focus on chips for ultra low power. Why? Because the local devices that go into wearables, you want them to drain very, very little battery power, right? So that's the reason you need ultra low power. And there's opportunity then for process technology enhancement, for circuit techniques, for modeling techniques, for packaging techniques, all of those things, there's opportunities. Bioenergy harvesting, so I don't have a picture of this, but one of my clients, they actually have a chip that does energy harvesting so that you'd reduce the power drain. So it's a very energy efficient chip. And so in that example, they're selling chips, but they could also integrate the solution in that they could have a sensor. Application could be like a fire alarm, right? And the fire alarm is up there, somebody has to go change the battery every 6 months or a year, right? If they have their device that drains very little power, it's kind of like an everlasting battery. Do customers care about it? In my home, that the ceiling is 20 feet, I absolutely care about that. I'd rather not have to change that ever. But that's a solution opportunity that they need to put together, not just the chip. So that's an example where they could go from being a chip provider to a solution provider. Same thing over here. eEver is the company that makes that marker chip I was telling you about. They're happy being a fabless IC company. But if they want to do a solution, they got to go to the next level. And it's either them, or you could go contract with them, buy their chip, and integrate that on a package and put a solution together that gets you to market. And remember what I showed you about the value chain. The farther up the value chain, the more money you make. The eEver chip might sell for $1. Your dongle might sell for $10. Doesn't mean you get to keep all of the $10, but you know, you might have to pay another $1 or $2 for the integration. But that's the kind of example that you want to consider. It's non-compete. It's well, I shouldn't say non-compete because I'm sure there are other people thinking about it. But if you have a technology that's unique in the way you can package it on a board, in a module, as we'll talk about, then you could have some leverage. Okay. More examples in the home. There's all kinds of gateways, security, appliances. Again, one of the startups in my class were for developing a camera that goes in the doorway that detects whoever's come into the door and sends a message to your phone when there's somebody at the door. So even when you're not home, it may record that image and let you know that there's somebody at the door. Now, it sounds like a neat idea. Is there competition? Is there a need for it? You got to do all that research, right? But those are things that are, again, potential applications. And then, like I said, every company in trying to expand their own business are looking at all kinds of opportunities. It's not just startups. So here's an example for Skyworks as a company in California. They're drawing pictures of what the home is going to be like, how the appliances are going to link together, on and on and on, right? So I'm just throwing this out as examples of things that people are looking at. You then have to figure out where you want to play. You could go work at Skyworks if you like to go build a gaming console for them. Or if you go work for Skyworks, they might have you work on one of these, right? So that's the way that works. Now, if in the meantime you come up with a brilliant idea that plays into the home market, do your research and figure out whether it's worth doing a startup. Now, 5G, from a technical perspective, you know, it's the 2G, 3G, 4G, now 5G, right, is what everybody's talking about. It's lower latency, more capacity, more speed, all of the technical benefits. The problem is that in this particular case, the reach is getting so expansive because you're reaching into a medical, remote medical detection of illnesses, solutions and surgery. There's all kinds of things. And they require a lot of data transmission, low latency, so they can leverage the technical capability. But there are also some challenges that says once you start doing this, is there a liability? Is there a security issue? People hack that system. How do you feel when somebody is operating on your liver remotely and the system gets hacked and redirects where the surgery is actually done? So there's all kinds of implications that are non-technical, and I think in the bigger scheme of things, all those problems have to be addressed. And fundamentally, my question in this is, does the customer really care? Do they really care to pay the extra amount of money for the doctor to do this remotely or not? And if the customer says, no, I don't really care, I don't want to pay any extra, then maybe that thing will not survive. So just keep your eyes open. I'm not sure which way that's going to go. But again, for companies that are investing in 5G, there are all kinds of opportunities for engineering. and application and marketing and all of those things. So good areas for you to play in. Let's see, here's a chart from, again, 2016 IEEE. Kind of says the same thing that I was talking about, is lots more demand from a technical perspective, but also the social implications are important. Okay, so now I'm going to switch gear to another opportunity area, which is more in the traditional process technology, device technology, circuit design. So this is a chart of from Bill Holt that talks about how the industry has migrated from the 60s down to now, and it's looking at the node transition. So originally the devices used to be all bipolar. Anybody know what a bipolar transistor is? The NPNs and PNPs, those used to be the workhorse. In fact, when I went to graduate school, that was my thesis, was about operation of a bipolar transistor. They're very power consuming, and as people wanted to integrate more devices on a chip, you just couldn't do that with bipolar. And so the MOSFET device, the metal oxide semiconductor field effect transistor, that was invented in the early 70s. CMOS came along because the power dissipation on the MOSFET was also pretty high, and CMOS gave you a tremendous power advantage. So that was kind of the workhorse. Now this is still CMOS all the way here, but we've had to introduce new materials and new device structures in order to manage the scaling, as we talked about earlier. Now, somebody asked a question earlier about CMOS, right, to Professor van der Spiegel. I don't remember who that was, but I'll give you my opinion, is that I think CMOS is going to be a hard technology to displace because of the infrastructure that exists in the industry for building CMOS devices. I think that even if some new technology comes along, I think CMOS may still be the base, and then you might have some more advanced technology, whether it's a tunnel pad or whatever, in the future. So I don't think CMOS is going away anywhere anytime soon. Okay? Just my opinion. Okay, so as far as opportunities, there's all kinds of new opportunities. There's a history of what technologies have used. There's copper, there's low-K dielectrics from a process technology perspective. I'll show you an example on the R&D curve for copper. So just remember that copper here was a 2000 time frame. There was strained silicon, there's high-K metal gates, self-aligned vias, immersion lithography. And this is to extend the ability to define finer resolution lines and spaces. And then the FinFET device, double patternings, because the minimum resolution of this immersion was, in the 20 nanometer type of range. By doing double patterning, it adds mask levels, but it lets people define narrower lines and spaces. There's work function tuning. By the way, one thing that has happened that I didn't mention here, but there are now so many transistors on a chip that some people say transistors are free. What that does is it opens up, as a designer, all kinds of opportunities. You can create new devices and new structures because you don't mind using more transistors now. Because adding a transistor is not that expensive. In the old days, if you had a transistor and 1 micron technology, that was huge, right? It increased the area of your chip. Now, a lot of chips are metal limited, interconnect limited, and so as a user, you have the flexibility, as a designer, flexibility to add more transistors if you need to. In fact, a lot of chips, one of the things that, again, I hope Irvant is going to get into, is that when you're designing these tens of billion transistor chips, they will selectively place extra gates that are not used. And what they're used for is, so let's say you go through the entire process of fabrication and you find, whoops, I needed an additional gate here, or reconnect a gate or something. Now you got gates available, and those can be connected to fix a design problem at a later date without having to go all the way to the beginning of the mask. Because if you look at the sequence of masks, you start from 0 to the contact level, which is all in the silicon, and above the gate is all the interconnect levels. If you can have the gates, the base structure still there, and reconnect the top levels, you only have to do half the process. So that's a trick that people play sometimes to make corrections to designs. How did I get into that? Oh, yeah, double patterning. Okay. So the other thing I was going to tell you is that in the old days, thresholds or the VT for MOSFET device, there was only limited number. You'd have an enhancement threshold, a depletion threshold, and that was it. And then maybe you get a one extra one or something. Nowadays, devices may have 4 or 5 or 6 different threshold levels. And the reason to do that is that gives the designer more flexibility in designing circuits. For analog device guys, they may have different requirements than a memory device and stuff. So processes are getting more flexible to where you can do that kind of custom tuning of VTs. And the way you do that is by, one of the ways is not just by the ion implantation, but also changing the metal work function of the different devices. So again, these are very exciting things they never thought about when I was in the wafer fab. So entering now means you got to go understand how work function variation works by changing the metal content of the gate. Dual core, multi-core, processors, power gating. These are techniques to manage power dissipation, read-write assist SRAM. So, you know, a static RAM is usually 6 transistors. In the read-write assist, what you really do is instead of the load transistor, you can replace with a transistor that you could, a device that really can, instead of going from 6 transistor to 4 transistor, and again, all kinds of opportunities there for learning new techniques in circuit design and process techniques. Digital assisted analog, a lot of focus on that because it used to be that analog design was really very automated, very black art actually is what they used to call it. Now, when you have these 10 billion transistor chips that need a little bit of analog function, you got to automate that, and you got to do that in digital to make it more automated processing, and that's getting very popular. It's not as good as what a custom designer could do, but it works, right? So anyway, this is kind of a layout of all kinds of, you know, on the top, process technology innovations and design architecture innovations, and it just keeps going on. So again, when you trying to answer the question why I say it's exciting is if I was to go back and become a technical expert again, I would be delving into some or all of these activities and maybe new ones coming along. How they get implemented is you would work with your research folks, you would look at papers, you look at the problem and come up with a solution that, you know, your company may adopt, and that goes on to the next level, and you, the inventor, you get a patent on it, maybe you get a raise, right? So all kinds of interesting stuff that's going on. Well, this is an example where I think this is the number of threshold devices that are available on a 10 nanometer Intel device for different applications. If you want to read more, go to Bill Holt's paper and you could probably learn that. Significant power efficiency, gate delay, switching energy times delay is constantly on the way down, right? So people spend a lot of energy, a lot of focus on trying to minimize the energy because They're trying to get more gates on there and keep them operational and lower the power dissipation. Now, beyond CMOS, there are new sets of devices that people are looking at. What they're saying is that there's going to be silicon evolution to new kinds of structures, tunneling FETs, magnetoelectrics, spintronics, all those things are in the lab being looked at. I don't know that they will ever totally replace, but spintronics, for instance, MRAM is being looked at as a replacement for embedded SRAM. So you might have a base CMOS device with spintronic memory. So that's entirely possible. People are talking about maybe different architectures instead of the von Neumann architecture to get more efficient use of, let's say, neural computing, for instance, neural networks. And again, for replacing memory, could also be spintronic applications. So again, exciting area to be in, lots of challenges. So again, you're in the right space. Figure out what turns you on and stick with it. Now I'll give you an example for, if you were to have a CMOS process and try to customize it to do better analog A to D converters or DACs, what you need is transistors with better matching, low VTs, low leakage currents, drain extended CMOS for I/O circuits, isolated transistors, integrated passives. And so, by the way, this information you can get from this keynote speech by Bahai, 2017, just back in February. You can also go to the Solid State Circuits magazine. I think it's the winter issue. Every other year, we publish a series of articles that talk about the limits of technology and circuits that have been reported at ISSCC. And there are trends that they're very nice description of those. So I would encourage you to go look at that if you're interested. Here's an example where, at ISSCC you got to present the latest improvement in the speed and accuracy, right? So they monitor this trend, and if your paper is the best, then you get accepted, right? I mean, you got to be pushing some limits. It's very difficult to get in. But here's a trend that says you double every 3.8 years, and it just keeps going. But the problem is that it's the clock jitter that becomes the limiter. And so that's what this chart is showing. It's from Professor Merman out of Stanford, reported by Bahai. And so again, you can go to that ISSCC paper or the Solid State Circuits magazine to look at this kind of information for all the different areas, not just ADCs and DACs. So on this chart, I've summarized what kinds of structures are being looked at. I'm certainly not an expert in this, but I would look at Professor Kleis tomorrow to get his view. But this is information from IMEC on a previous ITF there. But I wanted to point out here is that the power supply voltage is being considered to go down. I think today it's 0.9 volts. Looking at 0.7, going to 0.5, and then less than 0.5. This technology is pretty much in production here, the 14 nanometer. It's a bulk FinFETs or the ultra-thin SOI, silicon on insulator. What's being considered is band engineering, tunnel FETs, graphene, spintronics, all of those kinds of things. I think if you look at the Bill Holt paper, they will talk about how they are on track to do the 10 nanometer and 7 nanometer at Intel. And again, just be careful that Intel 10 nanometer may not be the foundry 10 nanometer. So if you're looking at the detail, there's lots of fuzziness in there. Intel may claim that the other foundries are maybe a generation behind, but and then you get into all kinds of details about but the foundry customers like the Qualcomms of the world and Apple care about the interconnect density, and the foundries may be more aggressive there versus Intel. So it becomes really fuzzy, and get some experts to tell you what really makes a difference. Now, as far as the devices, there will have to be some changes here, and again, you could participate in the industry that helps define those by going and working at IMEC. Don't do a startup in this kind of stuff, and I'll tell you why in a little while. One, because it's very expensive, and two, because it takes a long time to get to market, and I'll show you an example of that. Okay. Let's turn to another opportunity, which is fabless, which is near and dear to my heart. Like I said, I've had lots of experience in the fabless world. In fact, if you look at the whole industry, industry used to have 3 pillars. It was the market applications, capability, and profitability. Remember I said earlier, every generation, next generation, the product has to be cheaper, more profit for the companies. They kept driving that on and on and on. And in the 90s, it came along that you got away from this concept that real men must have wafer fabs, right? In the old days, if you wanted to ship integrated circuits, you had to have a wafer fab, right? Then along came fabless in the early 90s, where there was a lot more designers in the world than there are fabs, and they're process engineers, by the way. And so that was one of the motivations in here. People that had the ideas, that wanted to ship their chips,